Okay, so now kind of wrapping up, now moving on to the cotangent function. And again, I think the easiest way to understand the cotangent function is to look at these coordinate points, because remember that the tangent of any angle theta is y over x. So the reciprocal of cotangent of theta is just going to be the x coordinate of the y coordinate. So what we remember from tangent was, it was undefined when x was 0, which was basically at pi halves and at 3 pi halves. We can see from cotangent here, cotangent is going to be undefined at 0 and pi. So rather than writing it again as 0 plus pi n, we can just write pi n. So the asymptotes is going to be at x equals pi n. And again, at every version of pi, so pi, 2 pi, 3 pi, 4 pi, we're always going to be ending up at being able to evaluate when the sorry about that. The x coordinate is 0. I totally messed that up. Tangent is, when the y coordinate is 0. Yeah, there you go. Just misspoke on my end. Sorry about that. So therefore, the domain, I did not copy down the right domain. So the domain is going to be all real numbers such that x cannot equal basically pi n. Oh, I did write the vertical asymptote. So that's going to be x equals pi n. The range, you can see that this graph is again going to continue and definitely going up and down. And then the period is again pi instead of 2 pi. That's when the graph, how long it takes the graph to repeat itself. So to look at this kind of like initial period here, when we kind of go around the unit circle here, we know that at pi n 0, there's going to be an asymptote. Oops, let's do it in purple. And then at our next point of pi, there's also going to be another asymptote. Right? And then if we look at pi halves, at pi halves for tangent, right here, right, that was undefined. That's y over 0. It's undefined. However, you look at it for cotangent, that's 0 over 1. So therefore, you can see that that is going to be a x-intercept for the cotangent function. Now, if you remember, the tangent function had a shape of a curve like this. And so if you kind of think about this as that mirrored image, that reflection kind of idea, it kind of makes sense then that the cotangent function is going to come in this shape like that. And if it doesn't make sense for you, another way that you can kind of work to explain this is to do those reciprocals that we did in the warm-up. Like take all these points, do take those inverse of them, and as you go through these quadrants, you'll notice that the first quadrant and the second quadrant is positive to negative, and that's how the shape of that curve works. You can see that these are positive and then it goes to negative. So it's going to go down in that kind of behavior. And obviously I showed you the link that you can follow that you can kind of investigate with the cosecant function. One other thing one other thing I wanted to mention also with this is, which I'm kind of surprised I didn't talk about before, but when we're looking at these graphs, remember, the trigonometric functions, guys, is going to be playing the exact same kind of role here. So one thing I just want to also talk about this relationship. If I have, let's give it the A sign. Oops, not 2. Why is that graph? Okay, so here's the sine graph. We talked about when we had 2, right? What that did is that vertically stretched the graph, right? So, and the same thing happens with the cosecant. When I change this to 2, you can see how that like mirrors the image of the cosecant graph. It's doing the same thing. It's doing that vertical stretch. What's important about this, what I think is helpful to understand like the domain and range of these functions is when you want to identify like the range of the graph, a lot of times you can just think of what the sine graph is looking like because you can see it's like that mirrored image of it. So if I wanted to find the cosecant, or if I wanted to find the range of 2 cosecant of x, I know that the sine graph is being stretched from -2 to 2. So therefore the cosecant graph is just going to be the mere opposites of that. And again, the same thing works here with other transformations. If I'm taking cosine graph, right? So here's the cosine graph. If I shift this up 1, that moves the graph up 1. In the same respect, when I take the secant graph, if I plus 1, that's going to move that up 1. So again, you can kind of I think it's easier to understand a lot of the transformations and apply them to sine and cosine, and then use them and then apply the reciprocal to identify the characteristics of your secant as well as cosecant functions. And the same thing with the tangent. I mean, whatever you do to tangent as far as, phase shift, vertical translation, and period change is going to be the same for cotangent. So just want to kind of mention that before we actually get into some examples. But what we will do is I'll kind of work through each one of the examples. One thing I did is for these examples is I provided a link for you that basically you can kind of follow along and check your answers to make sure that everything's going to make sense. So let's go ahead and get on to some examples.